I think
yeah, I think we can start.
Yeah, we can start. So first of all, we are really thankful, Professor Ikram, for accepting the invitation and having you here to present your recent result about your research. Just some, so as you can see here, the title will be Spectrally Efficient Multiple Access Design for Beyond 5G, 6G Networks and Exploiting the Deep Reinforcement Learning. Just some words about Professor Ikram. Well, he is very known to all the community. He is an IEEE fellow, professor at Electrical and Computer Engineering Department at the University of Manitoba, Canada. He received his PhD from the University of Victoria, Canada in 2001. He is widely known as a highly cited researcher for the last years from 2017, okay, as a highly cited researcher. A lot of research awards, paper awards. He has been editor-in-chief and in the editorial board for many journals in the IEEE. And well, the CV is known to all people that are in ComSoc and within the same area. So, Professor Ikram, thank you again for accepting the invitation, and we are happy to hear from you.
Yeah. Thank you very much. Thank you very much, Nizar, for your very generous introduction. I'm also very happy to be able to give this seminar today, and thank you for organizing this talk through your technical committee. So I again thank everyone for joining this talk today. So as you can see, I'm going to talk about multiple access design for next generation cellular wireless networks and some promises of machine learning, specifically deep reinforcement learning in the context of multiple access design. So Nizar, that's what I said. So it gets stuck.
Okay,
no, I think got it. Okay, sorry.
Okay, good.
Okay, sorry. So here is the outline. I will very briefly talk about the expectations from the beyond 5G wireless systems, kind of the evolution path that we are envisioning. And then I will talk about multiple access methods for beyond 5G systems. I will briefly talk about a few ideas that can be used to design spectrally efficient multiple access in future systems. And then I will talk about machine learning very briefly, though, specifically on deep reinforcement learning techniques, how we can use DRL techniques for multiple access design. And I shall give a specific example, like how we exploit DRL for multiple access design in a cell-free, what we call cell-free massive MIMO system before I conclude the talk. Okay, so we are in the 5G era, and 5G systems are being developed. I think very soon, or by this year, probably we'll see deployment of 5G systems, and a lot of work have already begun in the context of beyond 5G systems. So if we look back, like the evolution of cellular wireless networks, we started off with these single-tier homogeneous cellular systems. Then we evolved to multi-tier heterogeneous cellular wireless networks, which are basically 4G systems with a lot of technologies, small cells, relays, cloud RANs. Those are all discussed in 4G systems. And then we evolved to 5G systems with two new technologies, I should say, massive MIMO and millimeter wave technologies. So those are the two kind of big new technologies that were added on top of 4G, and that's what we call 5G. As I said, we are now thinking about beyond 5G systems. So if we think of the evolution path, we can envision there'll be new technologies like going beyond millimeter wave, like a terahertz communications, visible light communications. And also on the architecture side, we can think about the new system architectures like cell-free systems and integration of terrestrial systems with aerial systems, for example, like drone-based systems. And also maybe underwater systems will be also integrated with these terrestrial and aerial systems. And also on the architectural side, softwareization will be a key aspect. So SDNization of the network is not only the access network, but kind of a integrated end-to-end network will be softwareized. So, and from the energy efficiency perspective, we will see a close connection between networks, cellular networks, other wireless networks with smart grid systems, so that the energy efficiency overall can be improved. So to summarize, we are kind of heading toward what we call Internet of Everything, and we envision to see a convergence between terrestrial and non-terrestrial systems. Of course, we always need more capacity, more connectivity, and very high energy efficiency. And we will have a programmable kind of a network. It's not only the network, but also on the propagation side, on the wireless access side, we will see programmability, for example, through these intelligent reflecting surfaces and those kind of technologies. And as we have already seen, like convergence between communications and computing, like edge computing, fog computing, they will be part of the radio access network. A lot of research have already been done and are being done now. And as I was also mentioning, the virtualization through SDNization for more flexibility in resource allocation, more utilization of the end-to-end network resources will be crucial, and that will be possible through SDNization in a kind of a converged communication network. Well, so if we talk about the wireless access part, we envision a very high data rate, in beyond 5G systems, say in the range of terabit per second, when compared to several tens of gigabit per second in 5G. When we look back on 4G, our kind of requirements were in the range of 1 gigabit per second. So, I mean, for this kind of capacity, of course, as you can think, like we will need higher spectral efficiency, right? So we get to squeeze the most out of the spectrum. And also we will move toward higher frequencies like a terahertz and nanometer wave communication, optical wireless, visible light, etc. And on the architecture side, going from cellular to cell-free will be another potential technology. And actually in this talk, I'm going to talk more about the cell-free architecture that has a lot of promises in the context of improving the spectral efficiency. And again, on the architecture side, as I already mentioned, the integration of terrestrial systems with aerial systems, for example, by exploiting drones as mobile base stations that will improve the coverage and connectivity capacity of future systems. And again, to improve the spectral efficiency, connectivity capacity on the access side, wireless access side, we will probably be using these intelligent reflecting surfaces. Those will enable better channel quality to improve the spectrum efficiency. Okay, so so now in this talk, my focus will be more on the multiple access and how can we achieve higher spectral efficiency to achieve a rate in the range of terabit per second. Now, traditional multiple access schemes, which mostly use orthogonal multiple access like TDMA, FDMA, CDMA, even though FDMA may not be sufficient. And I think an obvious choice is to think about non-orthogonal multiple access. So basically, the same spectrum resource should be used for multiple users at the same time, right? So it will be like a non-orthogonal multiple access. And this idea of NOMA, which is basically power domain NOMA, has been already investigated quite a bit and has been already in the standard actually in 3GPP, in LTE Advanced, and also some other standards, and also in 5G new radio standards. So power domain NOMA has been already there. Now we will go beyond probably traditional NOMA and what I call like a massive NOMA. So in fact, there are potentials where we can use NOMA in a more massive fashion, and we can integrate with other technologies like a comp, etc., to basically get the most out of our spectrum. Okay, so I will talk about three concepts here: orthogonal NOMA, comp NOMA, and then cell-free NOMA. So this kind of a evolution you can think of. So three different concepts, and I call all of them to be like a part of this massive NOMA concept. Okay, so just to give you an introduction on this non-orthogonal multiple access, say on the uplink, right? So the concept is based on superposition of signals from different users. So if you have a two-user NOMA system, so basically they'll be using the same spectrum at the same time, and the receiver will exploit the power division, right? So for example, user 1 is closer to the base station compared to user 2. So say if they use same power, just for simplicity, for example, so most likely user 1's receive power will be higher than user 2 because user 2 is farther away. So the receiver at the base station can detect user 1 signal, right? And it can separate out from the composite signal, and basically that's how the signals for these two users can be detected. Okay, so the idea here is to use this what they call successive interference cancellation, so separate out the signals. Now if we do that, so the rate that we can achieve, as you can see here, like for user 1 we have a rate like this because he's like the stronger user. That user will be interfered by user 2, while user 2 will be like interference free because the stronger signal has been already taken out from the composite signal. So now to be able to do this successive interference cancellation, there is a requirement on the power difference between the two users. So on the receiver side, the difference between the received powers corresponding to these two users should be greater than some sensitivity threshold. So that will be required when we do SIC. Okay, so now this is like a two-user NOMA. So like a two users use the same spectrum resources. So you call it like a cluster. A cluster is formed by two users. So you can put more users. However, what will happen if you put more users, this requirement, SIC requirement, will become more difficult to satisfy. And there will be, the implementation wise, it will be more complex. So in reality, you may not be able to put too many users in a cluster, although you would like to do that, right? Because that will improve the spectral efficiency, right? Anyway, so the idea here is, again, is to use this SIC. So the receiver will decode the strongest signal and subtract the strongest signal, right? And then the rest of the composite signal, from the rest of the composite signal, you will decode the second strongest signal, subtract it. So that's how the successive interference cancellation works. And as I said, to be able to do it successfully, you need to have that power difference. That requirement has to be satisfied. And as I said, as the number of users increases, and with limited power budget of the users, it will be increasingly difficult to satisfy that constraint. So you may not be able to put too many users in a cluster. So then what can we do? So because we cannot put like a 10, 20 users in a cluster, right? Because that will make SIC very difficult. So one idea could be, well, why not we use multiple clusters while the spectrum is overlapping. So we can partially overlap the spectrum for the different clusters, right? So that's the idea of what we call like a overlapping NOMA. So two NOMA clusters can be overlapping in terms of the spectrum that they use. So this can increase the spectral efficiency, right? While avoiding, to have many users in the same cluster. So that's the idea of orthogonal NOMA. So I will not go into very detail because the results you will see in the paper that I show here. So basically, as I said, we can put less number of users in a cluster while we can still get higher spectral efficiency by overlapping the clusters. And of course, as you can probably guess, there will be a trade-off. There will be a trade-off between the cluster overlapping and the number of users per cluster. So if you put fewer users per cluster, maybe you can do more overlapping, right? If you put more users per cluster, you'll probably do less overlapping, right? So, for the same number of users per cluster, overall spectral efficiency can be significantly enhanced by increasing the overlapping percentage, which is also kind of obvious. So if you compare two systems with like non-overlapping clusters and overlapping clusters, of course, if you overlap clusters, your spectral efficiency will improve because you are freeing up more spectrum to be used by other users. But of course, implementation-wise, it will be a bit more challenging. Okay, so now another concept which has been already discussed in 4G systems, actually, this coordinated multipoint transmission. So if you recall, this idea is based on base station cooperation. So generally, the users who are in the cell edge, those guys are poor users, right? Because they are interfered by other co-channel base stations. So to help those guys, the idea of base station coordination basically came up, right? So basically, instead of creating interference, the co-channel base stations can help those users in the cell edge to boost up their SINR. So if you look at this figure here, so these two guys, U1, U2, are cell edge users. So now say if these guys were served by cell 1, then this cell 2 will cause interference, right? If it is using the same channel. So the signals from cell 2 will be causing interference, but instead, if this cell 1 and cell 2, they coordinate, they kind of agree to help this guy. So basically, they can, both of them can basically send the signals to E1 and U2, their signals. So basically, the SINR will improve because the user's signal power will get improved. So this is the idea of this joint transmission comp. Basically, two base stations, they will send the same signals for those cell edge users. So that's how the SINR will improve, right? Because instead of coming in the denominator as interference, the signal will be in the numerator now to improve the SINR. So now, if we combine this concept with NOMA as well, so these users could be, for example, like if you take for simplicity, just take one user, cell edge users. Now all these 5 users could be served in the same spectrum, right? And there could be 2 NOMA clusters, right? One cluster basically cell 1 and another cluster by cell 2. And this guy could be in both the clusters. So this is a cell edge user. So we are kind of combining NOMA with comp here to help those cell edge users, right? And just, if you think of the rates for user 1, so as I was mentioning, in the numerator of the SINR, now it got signals from both the base stations. So this will basically improve its SINR. And the interference that it receives is basically the Intranoma interference from the other guys, right? From the 4 other guys, right? Which are in the basically in the 2 clusters, but using the same spectrum. Now for the other guys, the non-comp user, I mean, this is like the same as before. The interference will come from the intranoma, like intranoma interference, because like the closer guy, as we saw before, he will be interfered by the further guys, right? If it's uplink transmission, right? So the closer guy is interfered by the further guy. And if there are other users, so the second guy will be interfered by the other guys, the weaker users. So that's how the interference comes here, the NOMA interference. And in this case, also intercellular interference is also like a due to NOMA because they're using the same spectrum. Okay, so now I'm not showing any numerical result here, but if you like what we have shown, this combination of NOMA with COM can also significantly improve the spectral efficiency of the cellular wireless system. Okay, so now going beyond even further, basically generalizing this idea of COMP, where multiple base stations or multiple access points serve a user, we can make it more general. How? Like going to this cell-free network model. So basically, you've got multiple access points scattered in a geographic region, and all the users could be served by all users. So basically, if you think of like a downlink, for example, so a user would be receiving signals from all the access points. It's like a COMP kind of scenario. In the uplink, same thing, a user signal will be received by all the access points, and then they could be all processed in a central processing unit, for example. So where multiple users can be detected. So their signals can be basically distinguished. Okay, so here you are exploiting full cooperation, like, right? So full cooperation among the base stations to serve users. So there's the idea of cell-free MIMO system, because here like a multiple transmitters and multiple receivers are involved here. So if you compare with traditional cellular, where a user is associated to a particular base station, here is not, right? So here a user can send to all the neighboring access points, and also it can receive from all the neighboring access points. So there is no like a fixed user to cell association here. So it's like a distributed single antenna system combined with cooperative MIMO, and that gives rise to cell-free MIMO. Okay, so now as you can see, when we allow all users to use same spectrum, right, then you will need to do some kind of interference cancellation, because at the CPU side, you go to detect the signals from each user, right? So so basically, we'll have a network, if you think of like this. So multiple access points serving multiple users. So you have got K users in a geographic area, and they are served by M access points. So all these guys are served simultaneously, you know, using the same spectrum, right? So first, if you want to see theoretically, like what kind of rate and coverage we can expect. So we did some investigation, and basically, okay, I am summarizing the results here. So compared to the case when you have got only one access point serving multiple users, it's like a traditional NOMA, right? So one base station or one access point serving 2, 4, 8, 16 users. Of course, as the number of users in a cluster, you can think of like number of users in a cluster increases, the coverage will go down, right? With smaller number of users, the coverage improves. So this is for the case where 16 users are served by one access point only. It's like a one NOMA cluster. While this one is for the 2 users. Of course, you know, it will be higher. Basically, the outage will be smaller, so the coverage will be higher. Now, on the right-hand side, if you see like the effect of access cooperation, base station cooperation, so you have got 16 users served by say 1, 2, 3, 4 access points, right? So it's like a cell-free NOMA system, and you see as you increase the number of access points, with 4 is the highest kind of coverage or lowest outage, and for 1 is the highest outage or the lowest coverage. So indeed, like cell-free NOMA can cell-free NOMA can improve performance, but of course we'll need a method to do interference cancellation. Now, the SINR for each user in this kind of scenario can be expressed like this. Now the numerator is basically the user's power. Now this W is basically the beamforming weight. Now each of these access points, if you go back here, so each of these access points, they receive signal from all users, right? And they will send this composite signal to the CPU for detection. Now, so basically each access point will have to figure out a beamforming vector, right? So for example, if you have got say 10 access points and 5 users, so each access point has to send a 5 element vector, which is the beamforming vector to the CPU, right? And these are those beamforming weights actually for say WMK is from access point 1 for user K. So if you have got 10 access points, 5 users, so basically each of the access points has to send a 5 element vector, right? So if we can optimize these beamforming weights, basically we can optimize your SNR and our capacity coverage. Okay, so if we use basically using the successive interference cancellation, so gamma K, the SINR can be actually written like this. So if you look a bit carefully here, so in the denominator, basically the interference will come from the users which are kind of relatively poorer quality. So same concept as we saw in like a traditional NOMA, right? So now the question is, okay, so how to choose these W values so that we can optimize the gamma K. So to design this system, right, so we got to optimize these beamforming weights. So there's the problem, like there's the design problem in this case. So to optimize our multiple access. So the problem will be this. So this is an optimization problem to optimize the beamforming weights from all those access points. Well, so without going into very details, you can see from the objective function, this is basically sum rate maximization, right? If you've got K users for spectral efficiency optimization for all those, sum of the spectral efficiency you want to optimize. And this constraint is basically SIC constraint, okay? So to be able to successfully decode the signals at the CPU, you need a power difference. So that's what this constraint is about. And beamforming weights between 0 and 1, okay? So, so that's the optimization formulation. Now, this is actually a non-convex optimization problem, okay? So, if you are familiar with optimization theory, you know, like for any non-convex problem, the optimal solution, the truly optimal solution can only be found by an exhaustive search, which in this case would be infeasible in a practical system when your number of access points and or number of users increase, you know. So I mean, you cannot really do it in every time slot, for example, right? You need to find this beamforming weights in every slot, which may not be feasible to do. So that's where the idea of using machine learning actually comes. So what I'm saying here, machine learning formulations can be used to solve this kind of non-convex problem. So we are saying that, okay, if we have got non-convex, complicated optimization problems, machine learning can help, okay? So machine learning as a tool to solve optimization problems, okay? So now, very briefly about this idea of machine learning. I guess many of you already know about machine learning. The concept in data-driven machine learning is you train a machine, right, which can basically perform a mapping accurately. So machine learning is all about learning a mapping function, right? So for example, in image classification, right? So you are training a machine to identify different kinds of images, dog, cat, whatever. So what do? Basically, you train the machine so that when you give input, say a picture, an image of a dog, it can classify it correctly, right? So it's basically doing a mapping, right? There's an input, and inside the machine, there's a function that maps the input to the output. So machine learning is all about learning this mapping function. So a function that you want to learn. Now, the optimization problems are actually also, it's kind of a mapping, because when you have an optimization formulation, you have some optimization parameters, given values, and there are some unknown parameters which you want to learn. So basically, you give input those parameters, and at the output, you would like to know those optimization variables. But of course, you go to train, right? So if it is a data-driven supervised machine learning, you go to train the machine to learn that mapping, right, from input to the output, okay? And if it is a data-driven supervised machine learning, you go to actually generate those data. You need to indeed solve the optimization problem offline maybe, and then use those data to train that machine so that after training, you can basically use it, right, for inference, right? Now, the problem arises when basically you cannot even solve the optimization problem. It will take probably years, right? I mean, if it is a large-scale optimization problem, so generating data will be extremely difficult. So you can train. Now, what to do? So in those cases, basically, you can use reinforcement learning or deep reinforcement learning. So when data sets cannot be made available, then reinforcement learning technique can be used. Again, you basically train your machine so it learns without any a priori data, but interacting with the so-called environment, right? It learns that mapping by interacting with the environment, and after it learns, then you can use it for inference. So basically, you can use the solution online, right? So you don't need to solve an optimization every time slot. So it's something that is implementation friendly. So that's the kind of a key motivation, like you can find a solution that you can use actually in your practical system. Of course, this is not an optimal solution. Okay, there is no guarantee that you will have an optimal solution, but as long as if you can design your machine so that it gives a good suboptimal solution, that works. Okay, yeah, so that's what it mentioned here. So there is no performance guarantee because the mapping that you learn may not be, very, very the ideal mapping, right? So if you're happy with suboptimal performance, right, if you don't mind, then you can use it. And the biggest advantage is you can use it online, right? You don't need to solve the problem. So, I mean, well, you can argue I can use it as random, but in most cases, these algorithms will run give better than random kind of algorithms. Okay. Okay. So so now very briefly about this reinforcement learning, as I already mentioned, an agent. So in this case, our CPU, for example, like who basically needs to know those beamforming weights, or if you can say, okay, even the access points, maybe they learn those beamforming weights, right? So either an access point or the CPU can learn those weights by interacting with the environment. So is basically aligning a policy. If you want me to say in one sentence, it's all about learning a policy. So the system has a state, like for example, it could be the SINRs of the users for a given, say, beamforming weights. So these are the states. Now, or given channel fading coefficients, right? And then you basically have to figure out what should be the beamforming weights to give you maximum SINR or maximum rate. So it's learning a mapping from state to the action. So action could be the beamforming weights, and state could be the user's SINR, right? So so it's all about learning this policy. Now, for each state and for a given action, you can define what is called a action value function, right? So if I'm in a certain state, if I take an action A, what kind of reward I can get? So that's basically the action value function gives. Now, this for a certain state, for a certain action, I can have a maximum action value function for a certain policy. So policy basically means in each state what action I take. Because when I take an action, the system can evolve to a different state. I take certain beamforming weights, so this will give me another SINR, right? So basically, I give I get a new state. Again, in that state, I take an action. So that defines a policy pi, right? So over some time horizon, I can find the accumulated reward, what is QSA for a given policy. Now, over all the policies, right? If I get basically, I have one policy that will give me the highest action value function. So that's basically Q star SA. So basically that defines in certain state S, if I take A, this is the maximum reward that I can get. Now for different A, you will have maximum Q star, and you will choose the action which has the highest Q star. So that's the optimal policy. Okay, so it's all about learning this optimal policy. Okay, and as you can see, so this you can think of like a learning a table. It's like a two-dimensional table, right? So you've got a bunch of states, and in each state you can take certain action, and you can, if you know those QSA values, then you have learned the system, right? So, and then next time I give you a state, and you can decide which action to take by looking at the table. You go to that row, right, state, and see which action has the highest Q star as a value. So that's the action you should take, right? Because that basically the optimal policy. So now this is reinforcement learning. Now a problem arises when your S is a continuous, for example, or you have too many states. Then this kind of a tabular interpretation is not convenient. So then you go to this deep reinforcement learning, where you instead use a neural network, right, to map your state to action. So if you use a neural network where the input to the network is your state, say for example the SINR, and the output will be your beamforming weights, right? So then basically this neural network does the mapping, right, from state to the action. So that's how a deep reinforcement learning network looks like. And then, well, if you know the action, these are like, you can think of QSA values here. So you will take action which is the highest value. You take the action, well, the environment can change, and then you see the rate, and you can, based on the new state, you can take another action. So it can go like this. So now I'll use two slides to talk about this neural network if you are not familiar. So, well, so this slide shows the difference between the reinforcement learning and the deep reinforcement learning. So in reinforcement learning, we are learning this table, that is like a 2D table. We learn by exploitation and exploration. They're like a simple algorithms called epsilon greedy algorithms, through which you basically learn this table. But as I said, when your states are like a continuous, or you've got a huge number of states, then it's not that convenient. So you go to this deep reinforcement learning model where the neural network. So this is a neural network which takes the state as the input and produces the, say for example, the action values, right, as the output, right? So now this neural network again does the mapping, right? So this is all about mapping from state to the action values. So now it can have multiple layers. If you have a neural network like this, inputs come to the input layer, and those inputs go to the first hidden layer, right? So these elements are called neurons here. These circles, they are called actually neurons. And these neurons, output from the neurons go to the next layer. So if you have an architecture like this, it's called a deep neural network, where you've got multiple hidden layers. And as I said, all it does is mapping again. So from your inputs, right, you take a n-dimensional input, and you can produce like a k output, for example, right? So it does the mapping again, right? So now these neurons, they can do nonlinear operations. So just quickly, we see how a neuron does. So this is like a neuron. It takes the input and take a weighted sum, right, of the inputs, and then it can add a bias value, and then weighted sum plus bias goes to a nonlinear activation function, and it produces the output. Okay, so so basically by using these neurons, you can approximate the function, right? So a pattern, right? I give you a pattern and you can tell me what the pattern is. So it's doing this mapping through these nonlinear operations. So that's what a neural network does, just to quickly recap. Okay, so now these DRLs can be of different kinds. The one that we have seen, actually, this is called a value-based DRL, like a DQL, SATSA. So they're like a value-based DRL methods where the state maps to the Q functions, right? So if you got a finite number of actions, so for each action, you know the Q value. Okay, so then, as I said, you can take the action which probably has the highest Q value. So these are like a value-based DRL. There are also DRL which are called policy-based DRLs, which basically give you the actions as output. Instead of Q values, say in our case, I give the SINR values and the outputs will be the beamforming weights, like beamforming weights. So directly they map state to the action directly. So it's called like a policy-based DRLs. And there are actor-critic DRLs, which are a hybrid of these value-based and policy-based methods. Okay, so in DQL, like if you think of a value-based DRL, we are using a neural network to approximate the optimal action value function. So I give the state, right, and it produces the optimal action value function, right, for each of the actions, right? So we get those outputs, right? So these outputs are like optimal action value functions. Okay, so and again, as I said, after you know these optimal action value functions, you can choose the action which is the highest action value, right? Okay, so now the problem with this value-based is, if your action has to be like a discrete, right? I mean, you have a finite number of actions. Otherwise, you could use the policy-based method. If you have a continuous action space, then you can use it, right? So you need to use the policy-based method. Now, this one here, DDPG, this is actually an actor-critic method, a deep distributed policy gradient. So this is what DDPG stands for. So this is actually a actor-critic based DRL, and it's actually quite popular. And it can handle this continuous action space. So it has got actually two networks. One is called like a actor network, and it's called the critic network. So I show you this figure here. So basically, this is like an actor network. This mu network is called an actor network, and it's called a critic network. So this actor network is a policy network. So it maps states to actions, and this Q network is a value-based network. So it actually takes state and action, and it produces the Q values. So it's a combination of both policy-based DRL and a value-based DRL. Now, even going further details. Now, each of this network has also like two parts inside. So, like the actor network, like a mu network, has a prediction network and another called the target actor network. Okay, same at the Q network. So this is the critic network. Inside it has a critic network or the prediction network, if you call it, and there is a target critic network. Now, the reason of having two is, if you see, we have a neural network, right? So if you go back here, even here, for example, so now the weights, like these weights here, right? These weights, we get to learn these weights to do the mapping, right? It all depends on what kind of values we choose here, right? The accuracy of the mapping will depend on these weights and the biases. So we get to learn this, right? We get to learn this, and generally it's done through this back propagation algorithm. So basically, say, okay, I give an image of a cat and I know this is a cat, right? So with certain weights, I'll see something here, and based on my ground truth value, I can calculate the error. So then I will try to minimize that error, right? I will basically do the gradient of the loss function and then accordingly update these weights. So in these networks, right, you've got this network. So we get to do the back propagation. Basically, we get to update the weights. Now, where to get the true values from? I mean, so that's why they use another network inside, which is called the target critic network. That will give you like the target values, so that you can calculate the loss function and then you can basically back propagate. Okay, so high level, that's the idea here. So you need two networks inside each of these networks because you need a target to do the back propagation to update the neural network weights. Okay. Okay, so again, going a little bit more further, the actor network actually calculates a gradient like this. Okay, so the gradient, because if you are familiar with stochastic gradient or other, like a gradient-based algorithms for optimizing convex functions, etc. So, you need to do this gradient update, right? So in this case, the actor network uses this gradient, okay? Gradient to update the basically the weights inside the neural network, right? So now why does it look like this? Because what it tries to do is actually tries to maximize the action value function. Now this depends on the weights of the critic network as well as the weights of the target network. That's why it's like using the chain rule. I mean, that's what you will get, okay? And on the actor network, okay, so this is what I said for the actor network, okay? The gradient is based on this. Now, you do a batch gradient actually, so you have to take the average of the gradients. You take, say, n samples, right? So you get n gradients, and then you take the average of this n gradients. So this is called a mini batch gradient. Okay, so it's the same thing. So this is the idea of what they call deterministic policy gradient. So because using this gradient, they will update the weights of the actor network. Now, the critic network uses this loss function value to update the weights using back propagation. So anyway, and in the target network, they periodically copy the values of the prediction network. So so basically using these two equations, so those target network values, they remain still, but occasionally they will be copied from the prediction network. Okay, so using this what they call Polyak averaging. Okay, so that's kind of a little bit detail about how this DDPG architecture looks like. So in our case, let's see the example. How do you use this DDPG network to do this beamforming optimization? So in our case, the state, we get to define the states. So states are the user SINR, and the reward here is the sum of the user's weight, and action is the beamforming matrix. So this is the architecture. So as I said, we got a critic network, which is called the Q network, and an actor network, which is the mu network. So the actor network takes the state as input and it produces the action. So because it's a policy network, right? So it produces the action directly as output. And then also you see the this action will be going back to the critic network because it takes the state and the action into, as inputs, and it produces the Q values. And the gradient of the Q values, that will come also back to the actor network, right, to update the weights of the network. So the policy gradient, to calculate the policy gradient, it needs this Q value here. So this is the architecture. And now also you will see a replay buffer. Basically each time you give a state, there is some action output. So this will all go to the replay buffer. So the previous experiences, everything are stored in this replay table here. And you take the batches, mini batches from the replay buffer, and then you basically do this back propagation, etc. Okay, so in our case, as I already said, our state SINR output the beamforming matrix. So actor network will take the SINR values. So if you have got 5 users, so you've got say 5 SINR values, and you've got say 8 access points, right? So the state is like a 5 values, and action is the beamforming matrix, which is called 40 elements, because if you've got 8 access points, each access point has to generate like a 5 values for 5 users, right? So you've got a 40 values. So the matrix has 40 elements. They're all like real numbers. So the actor network will take 5 inputs and produce like a 40 values. The critic network take both the state and the action. So 5 SINR values, and the action is 40 values, right? And it will produce the Q value. Okay, so this is how the architecture will look like in our example here. Okay, so I think that's kind of a high-level description of the network model and the DDPG architecture. For the details, I would refer to the paper here. Basically, oh, sorry, I think I didn't mention here probably. Oh, the paper is not cited here. Anyway, so so that's the DDPG model for our beamforming problem. So I show you some results here. So so what happens as you train basically the DDPG network will learn, right? And when it learns the policy, right? So you get a kind of a stable, like it stabilizes. So that's where it basically converges. So you kind of learn the policy. So after you learned it, then you can use it for inference. Every slot you can basically give the state, and it will give you the desired action. Now, 2 other graphs I did not describe here. So these are like kind of other benchmarks actually. So this is the black one is the one that that I have described, but you can have also variations like you can do distributed learning, and also you can gather experiences distributedly from the access points. So that's like another option, D4PG. Due to the time constraint, I don't think I'm going to talk about these 2 other variations. So you can do several other variations in this learning process, but with a centralized learning where basically the CPU is running this DRL. So this is what you see. So basically, after it stabilizes, it has finished the learning, and you can use it for inference. Okay, so I think I'm going to finish here with these final remarks. For future cellular wireless systems, cell-free NOMA is a potential technology which can significantly enhance the spectral efficiency of wireless systems. And of course, we can use NOMA with other technologies for millimeter wave, terahertz communication, visible light communications. And also, NOMA can benefit from RIS technology, because one thing I mentioned at the beginning, the relative channel gains of the users, that's kind of important in the context of NOMA capacity. So if you can program the environment so that you can kind of have the channel gains the way you want, maybe through this RIS, right? That will improve the NOMA performance. And you can use NOMA with drone-aided communications. Now, when you integrate with all these systems, the problem of multiple access resource allocation will be more complicated, a lot of variables, and using traditional optimization may not be feasible for practical implementation. So machine learning techniques have promises. So you can use machine learning techniques to have solutions, some kind of good suboptimal solutions for those problems. And in all those cases, your modeling will be very problem specific, and for a problem, you go to customize your deep reinforcement learning model, and many of the state-of-the-art DQL techniques can be leveraged. And after you design, of course, the hardware implementation will be also important. So to have the complete kind of research, so we need to also focus on the implementation. Thank you, Nizar. So I think I am done here. Any questions?
Thank you very much for really enriching the presentation. The topic very interesting. We received some questions here from Ahmed Najib. He says, in your opinion, Professor Ikram, what are the main challenges for adopting deep learning, based approaches in a practical setting of resource management and cellular networks?
Okay, so
from a practical point of view, so from a practical setting, how feasible do you think this is doable?
Yeah, so as I said, I mean, DRL has a lot of promises, and for scenarios where your action space is discrete or, even if it's continuous, in both cases, you can adopt DRL approaches. Now, I think the challenge is more on the customization. I mean, it's like how do you customize your DRL model? Like how do you choose your neural network, right? So how do you choose the hyperparameters? How many layers and how many neurons per layer? So those like a hyperparameter optimization. That's actually more an iterative process. You need to trial and error, kind of. You test and see with different, selections. So I mean, I think it's more like a customization of the model. But as I said, I mean, that is something that will give you a practically implementable solution, Otherwise, you will just do randomly, things do randomly. I mean, those optimization problems, you cannot solve in every 5 milliseconds. No, it's like impossible to do. And even like estimation of channel and those kind of things can be done through machine learning. Then basically you can reduce a lot of like a signaling and complexity and other things overhead. So, actually ML has a lot of promises, especially the deep reinforcement learning has a lot of promises. So you have to basically set up with the model, the environment, and then you use all these software tools, all these platforms available. So it's more like developing the system model and the environment, right? And then customize it, and then all these tools are available. So this is, I should say, something that I mean, possible. And only challenge again is more like a customization of the network, the hyperparameter optimization.
Yes, I fully agree. We have another question also from Ahmed Najib. He wonders about cell-free design. So from the mobile network operator, do you think that many changes they will be implemented if they go for the cell-free setup?
Yeah, of course. Like now, one big issue will be like a backhauling, right? So all those access points. So how do you connect to the CPU? I mean, that's like a backhauling problem, right? So now those setups will be in a dense, kind of a environment where you have a lot of users, right? And you need to have high connectivity and capacity. I think in those scenarios, cell-free system will make sense. And of course, nothing is free, right? So you got to invest on the backhauling. I mean, right? So, but the wireless part, I mean, basically you can squeeze the most out of your wireless spectrum by spending more money in the backhaul.
Yeah, it's a trade-off. Where do you want to spend more?
Exactly. So wireless, exactly. Nothing is free, right? Yeah.
For sure. Yeah. A question from Burak. He says that what are your thoughts about the feasibility of empowering deep learning in drones, in aerial base station assisted edge computing? So do you think this is also feasible, or its complexity is more than whatever it can be allowed?
Actually, you see, I think there's a misconception here. DRL, you can do offline. I mean, in many of the cases, let's say in these kind of problems, I mean, you don't really interact with the environment. What you are doing, you are actually searching in a state space. You're looking for different options and you plug in the values and see what kind of a scenario you get, right? So you see, so this can be done offline actually. I mean, when you say complexity, computationally complex, I think this is a misunderstanding. I mean, you see the neural network, right? This is some simple addition and multiplication kind of operation, and this nonlinear, you know, like that activation function. That's all it is inside, right? Well, of course, if you make it a big network, but it's not like a matrix multiplication, inversion. You don't have those kind of things here, you know. So it's all like a linear, mostly linear kind of operation, except this activation function where you have, you know, non-linearity. So, and if you can do it offline, actually, so after you train the machine, you know, then you use it for inference. So, not necessarily like you get to train this all the time, and well, you periodically you will train it, but it's not like every slot you're going to train the machine. No.
Yeah, and actually this is another question from from Muayyad Al-Ugali, that he says, how frequent, how much is the periodic offline learning? So how frequent the offline learning should be?
So you see, there is no common recipe for this. So it all depends on how is your channel changing and things like those. You know, I mean. I think this is more a trial and error game. You know, it's more like you know, you try with different choices. That's how. I mean, there is no like a fixed common recipe. I mean.
Yeah, for sure.
Yeah.
So one last question.
Well, I think Nizar, I didn't answer Burak's question. So, well, I mean, deep learning can be used, you know.
You go.
Wherever you want. I mean, you know, why not drone? I mean, sure. I mean, if you see a nice application where it makes sense. Now, I probably not mention in detail. You see, it makes sense to use machine learning for problems where you have these what is called algorithmic deficit. You have a problem, but solving it has huge computational complexity, right? A non-convex combinatorial problem, you know, where you have to only, I mean, if you want to find the global solution, you have to do the exhaustive search, which is infeasible, may take weeks, right? So you have what is called algorithmic deficit. So then it makes sense to use machine learning, right? If it's a simple optimization, why you go for machine learning? I mean, you can, if it's a convex optimization, I mean, you know, no point of going to machine learning, right? You can do it using traditional techniques. Or in situations where you can't even model the problem, you know, because say, for example, in a propagation environment, which is very weird, you don't even any idea what kind of, you know, propagation, like the signal reception you will have and things like those. I mean, the environment itself is too tricky, weird, you can model, then you can do data-driven machine learning, right? So you need to have justification of doing machine learning. It's not like using it everywhere with, I mean, it may not make sense, you know. So, so of course, if you have a problem where either you have a modeling deficit or an algorithmic deficit, and/or then it makes sense. You can justify the use of machine learning.
Yes, I fully agree. So it is not to replace, let's say, convex optimization, but whenever convex optimization is not possible or it is difficult to model, then we can. Yes.
Convex optimization, you can solve it. So you don't need to worry about, you know.
Yeah, for sure.
Put in CVX will give the solution. So why there's no point? It's ridiculous to go for, you know, right? Yeah.
Okay, so here we have another question. Muhammad Al-Hattab. Yeah, so it's a repeated question. So whenever he asks for very dynamic scenarios, okay, so the channel changes a lot. Can we still apply deep learning?
That's a good question. In fact, even the lining phase, you see, what you can do, if you, during the lining, if you can capture variations in the channel gain, say in our example, like SINR, we are basically the state is captured in SINR. Now, SINR depends on the beamforming weights as well as channel gains, right? So, so basically during the lining phase, you don't need to assume that your channel gains remains constant. No, because they can change, because what we are looking at is SINR, right? So this SINR space, right, if it captures your channel variations of all kinds, then you presumably will have a good lining. But you keep your channel gains fixed, maybe that's not a good lining because you're only lining for a given realization only. But during the lining, if you can accommodate all sorts of variations in the channel gains, then presumably you will have a good lining. You understand what I'm saying? So in the lining, if you can accommodate different kinds of variations, so it will work. Yeah. Otherwise, okay, say maybe your lining, you have constraint on the lining period, or for some reason, then you get to periodically line for different kind of channels. Yeah.
Yeah, making it very specific will not make it work. Yeah.
Yeah, will not generalize, right? Your lining will not generalize if you have only limited channel realizations.
Yes. Really interesting. The usage of machine learning schemes to solve non-convex optimization problems.
Exactly. So Nizar, my message is this. So as engineering, as engineers, now we are not doing same thing as like computer vision guys. No, we are mostly, our problems are optimization problems. Am I right, Nizar? So
yes.
The message is, how can we exploit deep reinforcement learning to solve optimization problems, non-convex problems? So that's the kind of the point here.
Yes, very interesting point. And as you said, is we want to reuse it as a technique. It is available technique. Definitely, we will not innovate in the machine learning itself, but we want to use it to solve our problems.
Right.
Yeah. Very interesting, and very. It gives really new ideas. The similar.
Actually, even the machine learning community, they are also talking about these now. Basically, solving optimization. Yeah. I tell you. So this is a new kind of direction that even in the machine learning community, they are trying to explore, especially in combinatorial optimization, because if your action space is too huge, right? So think about this, those value-based methods. I mean, this is how good they will be if you have a huge action space, for example. So for combinatorial optimization, how can you do like a good solution in DRL? So this is like a problem that now trying to address themselves.
Okay. Okay, good. So Muhammad Al-Hattab, he is asking, non-convex problems can be transformed to convex.
Okay, well, but then you're solving the original problem. You are kind of, so this is what we do traditionally, right? Given non-convex problem, we try to convexify. So we are no longer solving the original problem because we're making approximations and removing some assumptions, etc. So in many cases, we are not solving the original problem.
Yeah. I think that he also might think about whenever all technique of relaxing the convex problem, so that we try to make it fit into some kind of convex or
exactly
approximating. Yeah. But I think that deep learning will provide a more general solution.
Yeah. So maybe you can get a better solution. You may customize your solution, which will be better than those solutions.
Yes.
Then you can sell it, right? Then you can say, well, look, my solution is better, right? Of course, if you have a worse solution, nobody will buy it, right? So you got to show that your deep learning solution is better than the other existing solutions to be able to sell it, right? Yeah.
Yes, for sure. Okay, so I think we don't have more questions. Okay, so no, sorry, there is one here. So Amr Muhammad, he is asking, if we make the training offline, how can we be sure that training environment mimics the practical one? It has not changed. So yeah, here is the I imagine.
Well, I mean, this is like depends on the model, of course. So in our case, we can check with different kinds of channel realizations, and things like those. Like it's more like a synthetic, right? I mean, way of doing it. But maybe it doesn't apply in other situations where you get to really exercise your action, right, in the environment. So, I mean, so it depends on the problem, I should say. But in many of the wireless problems, I think you can just, it's like emulating things, right? I mean, you can generate channels, right? Like you do in Monte Carlo, right? Of right? I mean, so like in our case, for example, as I said, when you get the new state, right, in each of these iteration, I mean, you can use another random channel realizations, you know, and then you calculate your SINR, right? Instead of just keeping your channel gains same, you can just change your channel gains as well, right?
Yes, yes, and to make it the more general possible as a solution for all cases.
Yeah. So you see, our intention is to find the mapping. Okay, this SINR, what should be our, kind of the beamforming factors, right? So yeah, so you can accommodate channel variations there.
Yes.
Learning,
Yeah, it is actually an area that I think that will generate a lot of results very soon, because there are still so many parameters to play, to optimize, and so on.
Well, I think, Nizar, I think, as I said, from the engineering point of view, it's more like a finding solutions to some of the problems which are previously too difficult, you know, too complex. People thought, I mean, we can, in practice, we can do this because too much computation. So that's kind of a way out, probably, to find some solutions to those problems, which were previously thought to be, you know, I mean, no hope of doing it in an online manner.
Yes. I don't know if you can take more of your time. We have one more question from.
It's okay. Yeah, go ahead. Sure, of course.
And he asked about the transfer learning. Okay, so do you think that is it effective to make this transfer learning across different transmission contexts?
Yeah, no, I think that's also a good idea. So that's another way of adapting to the dynamic environment. So instead of learning from the scratch again, right? Of course, I mean, this concept of transfer learning can be also done. Like, as I said, periodically when you learn, right? Periodically you do the training. So then, you know, learning from the previous learning episode can be transferred, somehow exploited in the next learning phase. Yeah, of course, I think that makes sense. Although I don't know the detail of this. But again, I think it will depend on the system, right? How do you, what information, etc. you exploit in the next learning phase. Of course, I think this natural way to think, right? Whether we can exploit our previous learning, right? Instead of starting from the scratch again.
Yes. So many interesting ideas came to mind that we can do, and
Nizar, actually, you see, the systems are becoming too complex. I mean, there are too many, you know, parameters, and you know, like these systems are becoming increasingly more complex, and using traditional optimization will be very, very difficult. I mean, they will be used primarily to benchmark systems, but for practical solutions, you will not be able to use them. You can also use them to benchmark your solution, maybe, but in practice, you got to find some efficient method to solve those problems. I think that's what will happen. You
know, this is the message. Yes, this is the general message. Well, so we come to the end. We really enjoyed a lot. So many questions. The presentation was really insightful. So
thank you, Nizar.
Yes, Professor Hossain, thank you one more time for accepting the invitation and having you here showing this interesting topic.